Welcome everyone. Today we are very happy to have Emil telling us about the Holar.
All right. So what I'm going to talk about today is the content of paper I put out last month, and something that will come out in another day or two, sort of following up the ideas. So let me begin. It's not forwarding the slide.
Oh. Of sharing. Yeah.
That's There we go. So let me begin with the obligatory slide on the black hole information problem. So we've been scratching our heads for just about 50 years now on a problem that was posed by Hawking, that black holes, when combined with quantum mechanics, are not black, but they radiate. But the radiation, if you calculate it semi-classically, seems to be emerging from the black hole horizon, where whatever is emerging is space-like separated from the stuff that collapsed to make the black hole. And so it seems like there's a conflict between or among the three bedrock principles that we use to build theories of quantum field theory, namely locality, causality, and unitarity. And it seems like we need to give up at least one of these in order to understand the unitarity of Hawking radiation. And the answer by the end of this talk will be none of the three that what we give up is effective field theory. Or at least that's my conclusion. What we would like to know is to understand both the unitarity of Hawking radiation, but also to get an understanding of what is underlying the thermodynamics of black holes. Black holes have an enormous entropy, which if you stick in the fundamental constants goes like 1 over h bar. And a temperature that's proportional to h bar. And so one way of thinking about black holes being black in classical physics is that you're taking the h bar goes to 0 limit. So the temperature goes to 0 classically, so they don't radiate classically. And the density of states goes to infinity. And so the question is, if you turn on finite h bar, where the density of states is finite and the temperature is finite, what's going on? Okay, and string theory has given us some beginnings of an understanding. If you like, one way of thinking about this problem is to divide it into two pieces. One where, because black holes have this enormous entropy, they're tremendous repositories of information, quantum information. Okay, and so first we might want to understand what's responsible for this enormous density of states. And then the question following that is what then, so once we understand, if you like, how to store quantum information in a black hole, then understand how to extract it and what's going on at the horizon. And so string theory has given us the beginnings of an answer to the first question: where is this enormous density of states coming from? By accounting for the microstates of black holes made using the various extended objects of string theory. So we can make black holes that are composites of, say, branes, say 1 branes, 5 branes, and momentum is the classic example first enumerated by Strominger and Vafa, where we can take a weak coupling limit where it's just counting some standard bound states in some gauge theory, and then be assured, because of various non-renormalization theorems in supersymmetry, that when we go to strong coupling, the branes source some ambient geometry through their stress tensor. And so we know that when the brane system is thermally excited, it makes a black hole. And yet, because of non-renormalization theorems, the density of states that you counted at weak coupling is preserved in the transition to strong coupling. So that's, if you like, a resolution in a particular example of this information storage problem. But it still doesn't tell us what's going on at the horizon of a black hole, because you did the counting in some weak coupling regime where there is no horizon. The horizon, if you like, is hidden underneath some kind of stringy effects. And so the question is, if you want to ask questions about what is local physics like at the horizon, then you need to analyze directly the strong coupling gauge theory on the branes. And so far, we don't have the power to do that.
This is also very closely tied to Susie.
It's also closely tied to Susie, or near extremality in other examples. In this particular example, the near horizon geometry is ADS3, and so there's a dual two-dimensional conformal field theory, and so there are, Carty theorems about what's the asymptotic density of states of that theory. So that doesn't rely on supersymmetry per se; it just relies on being near externality. So the system I'd like to focus on is a somewhat simpler version of this story, where we just take, rather than taking two kinds of branes and making a bound state like in this D1, D5 system, just take a single kind of D brane and wrap it on a and take n of them and wrap them on a torus. And so that makes some geometry in supergravity that's sourced by these branes. And for those of you who are not steeped in the literature, let me just take you through this, unpack this geometry a little bit. So we're dealing with some extended object. And so the natural object that couples to an extended object is the natural generalization of a gauge field. Gauge field coupling to point particles is, there's just an action which consists of integrating the gauge potential along the world line. So if you have an extended object that has some spatial dimensions associated to it, the natural thing is that its sources is an antisymmetric tensor gauge field, where the rank of the antisymmetric tensor is the dimensionality of the brane. And just like in a static, Coulomb potential for a point charge, if you have a p brane charge in 10 dimensions, it creates an antisymmetric tensor potential that dies off like some power of r with a coefficient which is basically the amount of charge, the number of branes, and some factors of the coupling. Okay, but the brane is coupled to supergravity, and so that gauge potential back reacts on the geometry, and there's some directions that are parallel to the branes and some directions that are perpendicular to the branes. If you think about the gauge flux that's being sourced by the branes, it's just analogous to electromagnetism. So if you think about electromagnetism, about the stress energy of gauge flux, the field lines essentially exert pressure. So in the directions transverse to the branes, the stress energy is pressure. So it wants to make the space expand. And so you see that here, if you come close to the source, then the metric is blowing up as you get close to the source because of the pressure being exerted in the directions transverse to the branes. In the directions along the branes, it's the opposite. The field lines are exerting tension. And so the geometry parallel to the branes back reacts against that tension to make the geometry shrink. Okay. And so that's a way of understanding, at least heuristically, where these various warp factors in the geometry are coming from. And we're going to be interested in black branes, so excited away from externality. And so as usual with any black hole, there's a factor of that is characterizing the horizon at some radius R0, where time slows down and stands still from the point of view of an observer at infinity, and correspondingly radial distances blow up. And so we can consider such an example for d pre-branes for any p, for p equals 3. This was the example that led to ADS CFT, where the near source geometry is ADS 5 cross S5. Where S5 is the angular spheres transverse to the branes, and ADS 5, the radial direction of ADS is the radial direction away from the branes, and the angular direction, spatial angular directions of ADS are the directions along the brane. Okay, and so one often, so the thing that led to ADS CFT was the realization that you can decouple this near source geometry from the rest of space-time by taking a particular scaling limit, which is basically sending the string scale to 0, keeping some ratio of the horizon scale and the string scale fixed. And so these days one thinks of the spatial directions along the brane as being a sphere, so that one gets global ADS geometry as the decoupling limit. I want to think of actually the original example of ADS CFT that comes out of thinking about string theory and brane dynamics, which is to compactify the branes on a torus, for reasons that'll become clear in a minute. Okay, and so the decoupling limit then is dual to a gauge theory. What gauge theory? Well, in the case of these three branes, it's just maximally supersymmetric Yang-Mills on a spatial torus. But that gauge gravity duality holds in for any dp brane for p less than or equal to 5. You can take a suitable decoupling limit and get a version of gauge gravity duality where maximally supersymmetric gauge theory is dual to some warped geometry in the bulk. And the reason I want to focus on toroidal compactifications is that in that case, the gauge theory has a Coulomb branch. Namely, in the gauge theory, this limit, R0 is some radial scale, and it's being held fixed in the limit. So I can take any of the scalars in the Yang-Mills theory and give them an expectation value, and that corresponds to pulling some of the branes apart to some distance in the transverse space, okay? And I want to keep that distance that the branes are separated to be, finite in this decoupling limit. So I want to take the scale of the Higgs vevs of the Yang-Mills, of the adjoint scalars in the Yang-Mills theory to be fixed in these units as I decouple the theory. And if you ask what does that correspond to in terms of the geometry that's dual, it's that you take the harmonic function that is characterizing this geometry, and instead of piling all the branes together at a single point in space-time, you just separate them a little bit in the transverse space. So now this this harmonic function, where is it here, becomes a multi-center harmonic function because it's harmonic. I can superpose solutions, then I get more solutions, and so so there's a version of the Coulomb branch in the geometry, and there's a version of the Coulomb branch in the gauge theory, and the claim is those are dual to one another.
So here, are you going to drop the ones in the previous expression? You have ones in your harmonic function.
So the decoupling limit is a limit where the ones go away.
Right, but you're keeping the ones.
So I keep the one in little f because that's the black brane. But the scaling limit that we're talking about is one where this term scales up to be huge relative to the one, and so in the limit you just drop the one.
So this is special to D1, D5, or
No, any of these DP branes, you can take the scaling limit. Well, you see it here. I'm sending L string to 0. So if I keep around G string and N, G string is going to turn into the Yang-Mills coupling, and it's just the number of branes I have. So
you're taking R small, right? So
I'm taking R small, and I'm taking it in such yeah. So then I have to keep Then I have to keep R fixed in units of L string squared. So if you trace through the decoupling limit, basically this term becomes infinitely big relative to this one, and so it's suitably rescaled radial coordinates. You're just dropping the one in the H harmonic function, but you're going to keep the one in the F harmonic function.
I see. So you rescale it so that R naught stays.
R naught stays, yeah, R naught stays fixed. That's
R naught doesn't stay fixed. I guess R
naught scales.
R naught scales.
R naught scales with L string.
Yeah. Okay.
Okay.
And R naught is your Coulomb. Is your going to be your...
R naught? Well, R naught is the black hole horizon, the black brane horizon radius.
Yeah.
But the point of the previous discussion was to say that in addition, you could put extra branes outside the horizon out on the Coulomb branch. Right. And so the question we're going to be interested in asking is, well, if there's a Coulomb branch, so there's a continuum of plane wave states of charged branes,
yeah.
How does that interact with the presence of the black brane?
So the extreme. So if you're taking the extremal case with a torus on your boundary, so the torus would shrink as you come into the interior.
Yeah. So well, think
about
the classic example is n equals 4 Yang-Mills, right? So in n equals 4 Yang-Mills, the limit you're taking is one. Well, yeah, you can see it here. So I drop the one in the harmonic function. Where is it here? Okay. So I drop the one in the harmonic function. So H is now just Q over R to some point. But it's H to the minus a half. So this factor is R over something to some power. So the proper size of these tori that the branes are wrapped on is blowing up as you go to spatial infinity in the decoupling limit.
Yeah, but I think we're worried about the other direction.
So you go in the other direction, yeah, they shrink. Okay, but they remain finite size at the horizon. So they'll shrink at R. They'll go to zero size at R equals 0. But that's inside the black hole, and I don't want to worry about that.
Okay. Yeah. So
So the geometry outside the horizon is completely non-singular.
Yeah. You have to have the horizon in there.
Yeah. All right.
Yeah.
Sure.
Okay.
And well, the kind of thing you're worried about is if I do go to extremality, then I'm looking at very near extremal black DP branes. That's the matrix theory limit, where there's a chain of dualities that relates these P branes to zero branes, a large number of zero branes, and their dynamics. And Banks et al. Conjectured that is a realization of M theory in flat space. Where this Coulomb branch is just the standard Coulomb branch, that I can separate things in flat space at finite cost and energy. So that Coulomb branch is just the statement that in flat space objects can move around freely if they're far enough apart from one another. All right. So I want to make use of that fact that there's this Coulomb branch and ask the question, what are the properties of Hawking radiation in this system? Okay, I have a black brane, so it Hawking radiates. But if I take the decoupling limit, I've removed asymptotically flat space. Okay, and so what we're really looking at is the sort of near horizon structure of the states of Hawking radiation. Okay, and in the case, say p equals 3, where it's just asymptotically ADS, we know what the wave functions are of any supergravity quanta that are living in the bulk. They all have wave functions that tail off and go to 0 at the ADS boundary. Okay, so everything that you would ordinarily think of as something that could be emitted as Hawking radiation is living in some kind of bound state, because ADS is like a confining box for gravity. Okay, but there's a Coulomb branch in the system, and so if you wait long enough, I mean the amplitude for emission we'll calculate in a minute, but if you ask what's the probability of emitting one of the background branes as a charged Hawking quantum, it's extremely tiny. It's suppressed because the branes are really heavy, but it's finite, and so if you wait long enough, it happens. And so because all the ordinary channels of Hawking radiation are in these confining states, the only way the system can decay is by slowly emitting the brane charge out onto the Coulomb branch. Okay. And so while I introduced it in the context of DP branes, you can also analyze this in the S dual of the D1, D5 system, which is Nuber-Schwarz 5 branes bound to fundamental strings. And that was actually the system I analyzed in the paper. We'll get to that in a minute, but let me just say a few words briefly in anticipation of the calculation we're about to do. So one advantage of thinking about the S dual Nuber-Schwarz branes is that there's a very well-developed worldsheet theory. So we can do not just supergravity, but perturbative string theory around the black hole background. And so this arises when, again, we're thinking about toroidal compactifications, and it's convenient to think about, well, so I'm talking about 5 branes, so they're wrapping some T5, but let's single out the one cycle of that T5, which is also wrapped by the fundamental strings, and call that S1Y. And then in the decoupling limit, actually, there is no singularity of the source. It's just that you have global ADS3 times S3 times T4, where, again, the radial direction is the direction away from the branes sources. Y is the direction that's wrapped by both the strings and the 5 branes, becomes in this decoupling limit the azimuthal direction of ADS3. And there's a T4 and an S3, which are not depicted here. But the Coulomb branch is just a continuum of what are called long string excitations, which can come in from the ADS boundary, shrink, and then re-expand, go back out to the ADS boundary. So we're used to thinking about gauge gravity duality in terms of the observables being some kind of boundary correlators. But in addition to boundary correlators, which are the appropriate thing for the supergravity excitations, there is this other sector of the theory corresponding to what you might call the Coulomb branch of fundamental strings. It's not quite that. David and I have heated discussions about this, but anyway, there's a continuum of long string excitations, which are the, if you like, the remnant of the Coulomb branch in the decoupling limit. And because there's a continuum and it takes infinite time for those wound strings to get out to the ADS boundary, that sector of the theory, the long string sector, as an S matrix is the appropriate observable rather than a set of boundary correlators. So now we'll be interested in thinking about the standard Hawking process. And one way of thinking about this that people often like to frame the problem in terms of is to think about vacuum pair creation near in the vicinity of the horizon, where one member of the pair gets off to infinity as Hawking radiation, and the other member stays behind inside the horizon. And that it's that way of phrasing things in terms of vacuum pair creation that directly leads to the information problem. That, if you think about creating a particle-antiparticle pair from vacuum fluctuations, that because it was created from the vacuum, it's in a unique state. That the particle and the antiparticle are something like a Bell pair in quantum mechanics. And so because it's in a Bell pair, the antiparticle is completely entangled with and totally correlated with the antiparticle. And so there's no information in this state, right? To have information content, you have to have, the system has to have the ability to be in a multitude of different states. And so the Hawking pairs have no information content on their own. And all you do when you separate them is to create some Bell pair entanglement between the emitted Hawking radiation and their partners behind the horizon. But once the black hole becomes more than half evaporated, the information that was in the original quanta inside the black hole has to start coming out. And the problem is that you've not been radiating any kind of information about what originally made the black hole. You're only radiating information about some vacuum fluctuations. And so to the extent that the vacuum fluctuations near the horizon are arbitrarily well separated for big black holes from the structure that made the black hole, which is sitting at the singularity, you can't radiate the information about what's at the singularity through such pair creation processes. That, if you like, doing so would violate locality in a big way, and causality, because what's at the black hole singularity is space-like separated from these pair creation processes at the horizon. So let's calculate the amplitude for this. I should say, well, let me hold on. So what we're going to be interested in is calculate the probability for a black hole or black brane to emit quanta carrying the various conserved charges, the energy, the angular momentum, the S3 angular momentum, the one brane charge, et cetera. Okay. And a very pretty way of phrasing this was elaborated by Wilczek and Krauss in the mid-90s, and then followed up by Parikh and Wilczek a few years later, to think about this pair creation process near the horizon as one where the way that the Hawking quantum escapes the black hole is by being pair created just inside the horizon, and the particle member of the particle-antiparticle pair tunnels out across the horizon and then runs off to infinity. Okay. And so what you're interested in then in doing is calculating that tunneling amplitude, and that should be the Hawking pair creation probability. Well, the amplitude U square is the creation probability. Okay, and so let's do a simple version of that. Let's just think about the classical action. So basically, we're going to calculate that amplitude like some WKB tunneling amplitude, with the particle starting just inside the horizon and tunneling to just outside the horizon. Okay. And so in WKB approximation, we're interested in evaluating the classical action on some kind of Euclidean trajectory, some non-classical trajectory.
Emil?
Yeah.
I'm confused because, yeah, you would go to Euclidean time and then compute there, but there's no inside the horizon.
I'm not going to go to Euclidean space. I'm going to stay in the Lorentz signature and just slightly complexify the vicinity of the horizon. You'll see it in a minute.
Okay.
So standard classical action for a point particle, some kinetic term, some mass term, some coupling to a gauge field. And okay, that's what I would write for a particle, but if I'm writing the same thing for a brane, it's more or less the same thing, just with more spatial directions. Okay, and so then let's work in some generic stationary metric near the horizon. I want to work in coordinates, not the short shell-like coordinates for which the RR component of the metric has a coordinate singularity. Let's do the appropriate coordinate transformation to something like Eddington-Finkelstein or some other system of coordinates which is regular at the horizon. And then let's pass from the Lagrangian form of the action to the Hamiltonian form. And because the Hamiltonian is just the generator of reparameterizations of the world line, it's a gauge constraint. And so the entire effect of the classical action is just what's sometimes called the reduced action, the integral of p dot dx along the trajectory. Okay. And the interesting thing is going to be the radial component of the momentum, and following that radial component of the momentum from just inside the horizon to just outside the horizon. And so the Hamiltonian, so when you pass the Hamiltonian constraint is just some function of the canonical coordinates and momenta. It's quadratic in the radial momentum, so you just solve some quadratic equation for P sub r in terms of all the other canonical coordinates and evaluate it near the horizon, because that's where the tunneling is taking place. And what you find is that is a kind of a universal result, that the radial momentum in the neighborhood of the horizon has a pole, which you can trace directly back to the fact that GTT has a 0 at the horizon. What's the residue of that pole? Well, you get a factor of the surface gravity of the horizon in the denominator, and then the various conserved charges that are carried by the quantum coupled to the appropriate potentials. So if you're looking at angular momentum, this is the angular velocity of the horizon. If you're looking at a charge, this is the gauge potential evaluated at the horizon. So everything is local in terms of horizon scale quantities, particular geometrical properties of the horizon that are involved in the first law of black hole thermodynamics. Okay. So here's the answer to Jeff's question. What am I doing then to evaluate? What I want to do is to evaluate the integral of PR dot dr along a non-classical trajectory that starts inside the horizon and ends up outside the horizon. And so I have to deal with this pole in some way. So the prescription that Wilczek, Krauss, and Parikh employed was a kind of an I epsilon prescription. You deform the trajectory slightly into the complex R plane, and you go around the pole at the horizon in the appropriate direction. So basically, you're using something like a Cauchy principal value prescription for evaluating this integral. But when you deform the contour slightly into the complex plane, you pick up half of the residue at the pole. And so, using the fact that the surface gravity is the temperature of the black hole up to a factor of 2 pi, what this thing is after doing the integral is just the energy minus conserved charges coupled to their various potentials divided by the temperature. And since all these conserved quantities are conserved, when this particle is emitted, it is subtracting the corresponding amount from the remaining black hole left behind. And so this is minus the changes in the corresponding conserved quantities of the black hole divided by the temperature. And using the first law of black hole thermodynamics, that's just minus 1/2 times the change in the black hole entropy.
Well, it doesn't depend on what the trajectory is. It just depends on the resident.
Just depends. Yeah, it's very, very universal. It doesn't care how you got out. It just cares that you got out. And and moreover, the amplitude for getting out is something very universal in terms of the black hole. It's just the change in the entropy of the black hole. Okay. Now, for ordinary Hawking radiation, the typical energy of the emitted quantum is of order the temperature. And so, this factor is order 1. And so, the amplitude is e to the is. So it's like e to the I something order 1 or e to the minus something order 1. It's not very suppressed. And so you have to start worrying about what's the prefactor in front of the exponential, and that starts being less universal. So the reason I'm interested in these charged emissions is that the charged quanta are heavy, and this exponential. So first of all, I've concocted a situation in which these charge emission processes are the only channel by which the black hole can decay. Everything else is in some kind of bound state wave function. And only these charged states that have a Coulomb branch are channels by which the black hole can actually decay in the decoupling limit. And furthermore, the emission process is exponentially suppressed by some macroscopic amount. And so the emission rate is extremely small, but it's finite. We just have to wait long enough, and the black hole decays in this way. So returning to the, what I just said is true basically for any of these black branes, any intersecting brane bound state on a torus that has a Coulomb branch. You can do this for. So in particular, it's true for, say, n equals Freudian mills on a 3 torus, dual to ADS5 cross S5 toroidally compactified. The particular example that's related to the situation where we have a world sheet string theory, the black branes have a near horizon geometry, which is just ADS3. The black holes are what are called BTZ black holes, which are just the garden variety ADS3 black hole geometry. Because it's locally SL2R, you can use group theory basically to describe everything that's going on, not just for particles, but also for strings. Basically, the dynamics of strings is just the dynamics in the SL2R Wess-Amino-Witten model times for the S3, it's the SU2 Wess-Amino-Witten model, and the T4 is just some garden variety T4 for perturbative string theory. And so the metric is just the standard killing metric. The anisometric tensor field strength is the volume form. And the BTZ geometry isn't quite global ADS3, it's global ADS3 is empty. You make the BTZ black hole by taking this geometry and quotienting by a particular discrete isometry, which is shown here. Okay, and so there's some global discrete. If you want, the BTZ geometry is ADS3 cross S3 cross T4, quotiented by Z. This is a hyperbolic element of SL2R, so its powers just replicate out to infinity. Okay. And in terms of geometry, R plus and R minus are the radii of the outer and inner horizons of the corresponding charged black hole. The charge, by the way, are right. So in what this identification does is it basically carves up the global ADS3 cross S3 cross T4 into a fundamental domain of that discrete identification, which looks like the Penrose diagram of the extended black hole geometry. And so if we want to ask, what are classical particle trajectories? They're basically geodesics on the group manifold, which then project down onto the fundamental domain of the identification. And so there are, for instance, trajectories that come out come out of the singularity sometime in the past, emerge from the past horizon for a little while, and then fall back in through the future horizon back to another copy of the singularity. Or if the particle has sufficient angular momentum, the angular momentum barrier keeps it from hitting r equals 0. And so it just sits there oscillating between a minimum radius inside the inner horizon and a maximum radius outside the outer horizon. There are also space-like geodesics, which just cut across from one boundary to the other. And if you ask, okay, what are strings doing? String solutions, intrinsically stringy solutions, in particular this Coulomb branch of long string excitations, comes when you do what's called a spectral flow transformation on the group element, corresponding to the classical particle geodesic. So you do this particular, so if you take the group element G that corresponds to the classical particle geodesic, and you perform this operation, left and right multiplying it, left multiplication by a function of the world sheet coordinate Z, and right multiplication by a function of Z bar. This now has some non-trivial dependence on both time and space. And so this is an intrinsically stringy solution. And when you work it out, it turns out to be winding the ADS azimuthal direction. And in the case of, say, this solution, emerging from the past singularity and ending up at time-like infinity. And so the Hawking pair creation process is one of taking two classical solutions, one corresponding to an antiparticle, which is just a particle running backwards in time, tunneling across to the corresponding forward solution where something is emerging and heading out to the asymptotic region. So this pair creation process is indeed one where this part and this part are just classical trajectories of azimuthally wound strings. And then there's some kind of tunneling process that's going on right at the horizon. And we know what the entropy is of the BTZ black hole. It's just matches the corresponding Cardy entropy of the dual two-dimensional conformal field theory. And the energy and the angular momentum in ADS3 are related to these inner and outer horizon radii by some standard expressions. And if you calculate, what is the change in the entropy of the black hole, which is what comes out of this tunneling calculation, it's this in terms of the energy and angular momentum of the string and how many times it winds around the azimuthal direction. And you see when the black hole gets bigger and bigger, the change in the entropy gets bigger and bigger, basically because this black hole entropy is itself secretly the entropy of the string. And so if you make the string shorter, you make the excitations on the string, they're waves in a box. And when you make the box smaller, they have more energy. And so for a given total amount of energy, you have fewer of them. And so there's less entropy. And so that's the sort of heuristic explanation for why there's a heavy damping for emitting wound strings. So, okay, so the first quantized formalism calculates this for us, and I maybe should have said but didn't, that that the thing that you calculate from the worldsheet expression as the tunneling amplitude is exactly what you get just by directly evaluating the change in the BTZ entropy. And so the tunneling amplitude is just this change in the entropy, so that it's half the change in the entropy. So the tunneling probability is just exponential of the difference between the initial and the final entropies of the black hole. And the way I like to pick this apart is to think of this as an inclusive decay process. I have an initial black hole. Okay, it's in some state. And then the final state is a smaller black hole with a particle outside the black hole. And there isn't much entropy in the particle states outside the horizon. So we can sort of ignore that. And the entire density of final states is coming from the entropy of the final black hole. And so of this difference in entropies, this factor e to the SF is just the factor of the density of final states of an inclusive decay process. And so how do I interpret this e to the minus SI? Well, in an inclusive decay process, it's this, what are you calculating? You're calculating the sum over the final states of square of the matrix element for the transition between the initial state and any of the final states. And so the role that's played by this e to the minus SI is that it's the typical matrix element of the transition. E to the minus SI over 2 is the typical matrix element. And this is further supported by a similar process that was calculated in the early 90s by Garfinkel, Horowitz, and Strominger, who asked the question, if I have an ambient, magnetic or electric field, what's the probability to pair create black holes, charged black holes in that ambient field? Okay. And what you find is an answer which is exponentially enhanced by the entropy of the final state black holes. That's the same inclusive sum that I was just talking about. And there's a suppression, which is, of course, the Schwinger amplitude for creating charged objects in an electric or magnetic field. And so this, in their calculation, this factor e to the minus S over 2 is replaced by the corresponding Schwinger tunneling amplitude for a pair of charged particles to gain enough energy in the ambient electric or magnetic field to go on shell. Okay. So there, it's that in their calculation, it's a very similar sort of structure. It's just that the transition matrix element is calculated by Schwinger pair production rather than this e to the minus S over 2 factor that we get out of this calculation. Now, this might remind those of you who are steeped in recent discussions of statistical mechanics of the eigenstate thermalization hypothesis, which says that if you have a simple operator in some kind of highly excited chaotic thermal system, then the matrix elements of that observable between energy eigenstates is given by some diagonal piece with some smooth function of the energy characterizing the VEVs of this observable in the various energy eigenstates. And then some off-diagonal matrix elements, which are characteristically damped by exponential in the density of states over 2. And again, then some additional smooth modulation of that. Times a random matrix, which is just a way of modeling the fact that you have some chaotic thermal system. And so I would say that the result here is a very similar statement, that we should think of the interaction Hamiltonian between the black hole interior and the black hole exterior as being something like a random matrix whose characteristic matrix elements between an initial state, which is the initial black hole, and a final state, which is the final state smaller black hole plus a quantum on the outside, as being governed by e to the minus S of the initial energy, and then some smooth factors and a random matrix. And that's consistent with the reverse process. So if we think about, this is some off-diagonal matrix element where the initial, as far as the black hole is concerned, the initial and final black hole are sort of far apart in energy and charge, because I sent out some macroscopic quantum with a lot of charge and energy. Okay, so this is a very off-diagonal matrix element for the black hole. You could ask, well, okay, if you're declaring that this is what that matrix element is, and everything is unitary, then there should be some adjoint process where so now my initial state is a small black hole with a particle outside. And my final state is a bigger black hole, which has absorbed the energy. And so that will be governed by just the adjoint of this matrix element. But now this factor in the adjoint matrix element is the entropy of the final state black hole. And so the matrix element is damped by this factor squared, but then it's an inclusive process, so I should sum over all the final state black holes that could get created. And this suppression of the matrix element just cancels the enhancement due to the density of final states. So the absorption, the adjoint absorption process is order 1, as you would expect for a black hole. So I think that says that this ansatz for what's going on microscopically is a reason. Okay. And so the black hole has this enormous phase space volume whose entropy goes to infinity in the classical limit. And so I think an interpretation of this is that I should think of black holes as being black just because the phase space in the classical limit inside the black hole is infinite. And so particle enters the black hole, it starts ergodically exploring this phase space. Because the phase space has infinite volume, it just wanders around and its probability to come back is 0. Right? And then when we turn on finite H bar, the density of states inside the black hole is enormous but finite. And so if you ask like, what's the probability of finding some energy leaking out of the black hole, it's just the ratio of the phase space volumes involved. That there's order 1 phase space for the particle outside the black hole, but there's e to the s phase space for it inside the black hole. And so if you sort of like grab the black hole at any random time and ask, is that particle inside the black hole or outside the black hole? The answer is, e to the s order, the probability of finding it outside the black hole is sort of like e to the minus s over 2. Probability is e to the minus s, the amplitude is so this sort of points to maybe that we should think of this issue of causality at the horizon as in terms of the underlying statistical physics, that the horizon is only a true causal barrier in the H bar goes to 0 limit, and that at finite H bar, it's just phase space probabilities. What's the likelihood of finding an excitation outside the horizon versus it being inside the horizon? Okay, but then, so this is of course what happens in the dual gauge theory, right? The dual gauge theory is just some thermally excited brane system, and there's some finite probability for things to leak off onto the Coulomb branch at any given time. It's suppressed by the fact that when you have a thermally excited non-abelian gauge theory, then the branes, which are essentially the eigenvalues of the adjoint gauge fields, are confined to one another by all the non-abelian excitations. In order to get a brane to come out onto the Coulomb branch, you basically have to de-excite all of the off-diagonal Yang-Mills excitations that chain it to the other n-1. So you have to have some very rare fluctuation where those off-diagonal gluons are fluctuate into some low excitation state, with the one brane having enough radial momentum that it sort of gets away. And that's indeed exponentially unlikely, exponentially in the amount of phase space that's available to all these non-abelian excitations. So, but it's still, there's still a question, what's going on at the horizon? Because ordinary matter, right? Ordinary matter has to collapse to the singularity. And so to the extent that these branes are just like any other ordinary matter, you would say, well, it can't sit there at the horizon waiting for all of the non-abelian excitations to turn off so that it can escape. Ordinary low energy effective quantum field theory would say any kind of matter you put at the horizon in finite proper time falls into a singularity, and then you have the Hawking problem. So, but the question is, a question I would ask is how much of this phase space diagram is actually germane to the physics? And we're already accustomed to chopping out various pieces of this space-time as being unphysical. So first of all, this system doesn't persist infinitely into the past. It's formed by some kind of collapse process. So we should at least remove the part of the space-time corresponding to the branes collapsing from infinity to make the black object. But there's also some analysis, some gravitational analysis from a decade ago, suggesting that this piece of the inner horizon is unstable to perturbations. Basically, while at the outer horizon, outgoing null geodesics are separating. That's why the horizon is thought to be vacuum. Is that anything you try to put at the horizon sort of disperses off and either falls into the black hole or escapes to infinity, leaving behind the vacuum state. But the reverse is true at the inner horizon. The outgoing null geodesics, the null geodesics that are going along the inner horizon are exponentially converging. And so, so any perturbation here you put there in finite amount of time becomes a kind of a null shock wave. And so these folks propose that you should really think of the inner horizon as being some kind of a null singularity. This piece of the inner horizon is a Cauchy horizon, because this is time-like infinity from the point of view of the boundary geometry. But in any case, we don't believe this part of the geometry anyways, because at finite h bar, you're going to be radiating out the branes, and so this piece of the geometry is supplanted by some outgoing state of charged branes. That's gone. And so the whole question is, what's the status of this region 2 between the outer horizon and the inner horizon? And if you believe that the outer horizon is some near vacuum state, then you would say, okay, the branes that collapse to make the black hole are sitting somewhere, out here at some singularity, and that's space-like separated from anything going on in terms of pair creation processes. And then you're back in the Hawking paradox. But the dual gauge theory doesn't have this problem. It's completely unitary. And so the question is, is the Hawking process really believable? And what I'd like to argue is basically some version of the fuzzball proposal that in the calculation we did, the tunneling process, it just involves some kind of geometric properties of the horizon. So in the effective field theory, the role of the horizon is to do the accounting of the microstates. It's the area of the horizon that's giving you the density of microscopic states. And in the tunneling calculation, it's the initial and final entropy that are also giving you the matrix element, as well as the density of states. So everything's going on at the horizon. And the problem would be entirely fixed if you said, well, the horizon is not some kind of vacuum state. but it's just the place where these microstates are emitting charged branes onto the Coulomb branch. And so, so what I'd like to suggest is that instead of a pair creation process going on at the horizon, instead you have something which is geometry outside the horizon, but not geometry, rather some plasma of brane excitations that, because they're sort of order n squared gluons in that plasma, but only order n to the 0 graviton states, that the gravity sector of the theory, which is some kind of collective dynamics of the gauge theory, is exponentially swamped by the e to the n squared other degrees of freedom that are outside of supergravity. And so, the properties of the horizon account in effective field theory for those microscopic degrees of freedom. But inside the black hole, those degrees of freedom are overwhelming the geometry. And so, and you shouldn't think of the interior as being geometric.
You're thinking about this as a smooth transition from a breakdown of GR as you cross the horizon.
I want to think of it as a deconfinement transition. So we know in the dual gauge theory that the transition between things that look like thermal gases of gravitons and things that look like black holes is a deconfinement transition in the gauge theory. And so, so I'd like to take that a step further and say that in the black hole, the horizon is to be thought of as a phase boundary, where outside the horizon, you're in the confined phase, where the only light excitations are the singlet excitations of the gauge, the collective excitations, which represent supergravity. And inside, it's this plasma of non-geometric gluonic degrees of freedom that are free to roam around. And that instead of the escape of things onto the Coulomb branch as coming from some kind of pair creation process at the horizon, it's this process of finding the rare occasions when that plasma of excitations de-excites in such a way that one of the members of the brane ensemble can escape. So the effective field theory calculation is calculating that probability for you. But it only cares about processes that are going on right at the horizon. And so I would say that what's going on inside the horizon is kind of up for grabs. And because the calculation I did only cared about the infinitesimal vicinity of the horizon. And so it doesn't make any claims about what's going on inside the horizon. And if you believe that what's going on inside the horizon is the antiparticle partner of the Hawking quantum in a vacuum spacetime, then it's a short step from there to the information paradox. Whereas if what's going on inside the horizon is some deconfined plasma of gluonic crap, then the Hawking quantum is emerging from that crap by some standard matrix element of a unitary system. And so the horizon, if you like, is not at finite h bar, is not a causal barrier, that there are processes that take you in both directions. And it's just that the relative probabilities are dictated by the amount of phase space that's available outside the horizon versus inside the horizon. It's not some untraversable causal barrier to emit something from the black hole. It's just entirely dictated by available phase space.
It sounds like you want to say though that GR breaks down at the. I mean,
GR breaks
it is
down.
it is a signal of GR no
Yes.
longer making sense,
And
regardless of how weak
Yeah.
the curvature is at the horizon.
right. And so and this is the current weakness of this fuzzball proposal. It's like, why should gravity break down in a regime of weak curvature? And I think the answer that's typically given is it's the available phase space of non-geometric excitations. That if it weren't for this e to the s, where s is 1 over h bar degrees of freedom, which are outside of geometry, then yes, you would conclude that the interior of the black hole is empty space until you get to near the singularity, where tidal forces are getting big. But if you know a viable alternative to that, until we disprove it, is that is actually the interior is not geometrical. Yeah.
Saying that you have a overwhelmingly high tunneling probability to a non-geometric interior, that doesn't rule out the tiny number of geometric interiors that still exist in the phase space, right? I mean, don't those still have paradoxes? I don't see how you resolve the paradox if you don't rule out all possible geometric states.
Yeah, I think that's sort of like the analog of the question of what's the likelihood of all the air molecules in the room going off to the corner, right? So if air molecules in the corner are the analog of geometric interiors, it's like that sort of question, and you would expect that those sorts of things would very rapidly decay into the rest. So I think the expectation would be that on something of order the scrambling time, such a state would become generic. I mean, this relies on matrix elements that we currently aren't unable to compute. But it's not enough just to have some configuration of things which looks like a geometry. It has to persist long enough for it to be reliably geometry for some period of time.
Mhm.
So you should think of graviton as being some kind of like quasi-particle excitation of this gluonic garbage. And the question is, what's the lifetime of those quasi-particles?
I guess another way of saying, I think I understand what you're saying, but another way of putting my question is if the probability to remain in a geometric phase is non-zero, however small, then you still, and the claim is there's a paradox, mathematical kind of inconsistency with those things persisting long enough. Well,
Yeah.
The probability is non-zero, there's still a paradox at the level of mathematical consistency. So you need to argue the probability goes to zero for those states to stick around.
No, I think all I need to argue is that well, yeah, I think all I need to argue is that that state decays on a time scale which is parametrically short compared to the time scale it would over which it would evaporate. Right. So I just need for the thing that you're positing to decay before it can emit anything.
Yeah, they needed to do that always.
Right, but the likelihood for the system to find itself in the state that you want is exponentially small, and it only persists presumably for an exponentially short period of time before it decays back into all the crap you assembled it from.
I mean, I'm agreeing in practice there wouldn't be a puzzle. I'm wondering if in principle, but maybe we can talk about it later.
I mean, how does this picture now jive with the original fuzzball counting of 3 charged black holes and actually finding star-like solutions for each one of them? Because those were still geometric solutions without a horizon.
Yeah.
You gonna stop the recording? Is it?
It's not-
The professional is coming.
Yeah, so, I think the current status is that the attempt to count microstates